Okay, here we are with part 2 of the Chapter 7 review. Hey, I'm a poet and don't even realize it. Sorry, old joke. Okay, what does a negative exponent mean? Two ways of looking at it. A negative exponent means, give me the reciprocal. Or the other way of looking at it, a negative exponent is very unhappy. If you get up close, you can hear them whispering, "Move me to the other side." A negative exponent desperately wants to be moved to the other side of the fraction mark. So we put the poor thing out of its misery, we make it happy, we give it what it wants, we move him to the other side, and we get x to the fourth. Please don't make that x to the negative fourth. Yes, believe it or not, I have seen students do that. But what does this now say? Move me to the other side. 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 And you get algebraic feedback. It's crazy. No, once it's moved, it's not negative anymore. That's silly. It becomes positive. Number 35. Well, in this context, yes, you could think of it as move me to the other side, which would give you a rather ugly result of 1 over 1/16 to the 1/2. But that's a pretty ugly way of looking at it. Better to think of it as meaning, give me the reciprocal. They mean the same thing. The reciprocal of 1/16 being 16, yes, just flip it, to the 1/2. It's still to the 1/2 power. Then you have to remember what the 1/2 power means. Well, hopefully you remember 1/2 power means square root of. The index comes from the denominator. Denominator is 2, index is 2. Of course, we don't normally put the 2 there. The 2 is understood to exist even though we don't show it. So we have square root of 16, which is 4. So the negative exponent says, flip me. The 1/2 power says, give me the square root. So we have 16 square root is 4. Number 36. For 36, again, negative exponent, move the whole thing to the other side. And by the way, I think we may have mentioned this in the earlier video, that negative exponent here does not say flip this fraction. No. It says flip the whole thing. So we end up with 8 to the 2/3. It turns positive over 1, but we don't care about the over 1 part, do we? From there, you can either just directly say, oh, I know what this means. It means to give me the cubed root of 8 and then square the answer. Yes. Cubed root of 8 is 2. Then 2 squared is 4. Done. Or you could write it out the long way and express it as, remember, denominator becomes the index, numerator becomes the power. Cubed root of 8 is 2, because, yes, 2 times 2 times 2 is 8. The cubed root of 8 is 2. Then we have 2 to the second, which is 4. Number 37, not assigned. The odd problem's not assigned. I tried to remember to put all the unassigned problems in yellow to make them stand out. The idea here is we borrow fractional exponents long enough to simplify this thing and then put it back in radical form again. So what do I mean by borrowing fractional exponents or rational exponents? We'll write this as x to the power becomes the numerator, the index becomes the denominator. But then, yes, we can reduce 2/4 just like you used to do back in 3rd grade. That becomes x to the 1/2. But then what does x to the 1/2 mean? X to the 1/2 means the square root of x. So we've taken this guy and simplified it all the way down to square root of x by making use of the fact that this can be written as x to the 2/4, which is x to the 1/2, which is square root of x. Nothing to it. Number 38. Okay, this guy. This is a cubed root. Do not miss that extraordinarily important little detail. It's a cubed root, not a square root. We don't know the cube root of 16, but we have to simplify it. Remember, we have in the back of our minds, oh, that's the front of our minds. We have in the back of our minds, and hopefully in the front of our minds, we have a list of perfect cubes. What are the perfect cubes? Well, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed is, I don't remember. Is there any perfect cube that goes evenly into 16? And there most certainly is, you say. It would be 8 times 2, because 8 is indeed a perfect cube. So I can paching it out, because I know the cubed root of 8. So I take it. Kapoom! Oh, there's a new word, kapoom. I've never used that one before. Kapoom! Or paching! The 8 pops out, becomes a 2 on the outside. What doesn't pop out? The 2 is not a cube, it can't come out. Now what about the y to the 6th? Well, here we can make use of fractional exponents if we want to, and think of this as being y to the 6 thirds. Well, what's y to the 6 thirds? Y to the 6 thirds would become y squared. We're done. Moving on to number 40. When you see a fraction like this, the first thing you might want to do is try to simplify the fraction. But I look at things here, 64 I can't simplify, x to the 6th no, y to the 8th, there's nothing I can do to simplify all this, I can't cancel anything. But wait a minute, let's move that z to the -4 to the numerator. Let's put it up here where it's much happier. And it makes us more happy too. More happy? Happier. So from there, we're now going to take this apart. We want the 10th root of 64. Well, how do we do the 10th root of 64? This is tricky. This is a little bit trickier than anything you would likely see on my test. Okay? But 64 is 4 to the 3rd power. Better than that, it's also 2 to the 6th, right? Yes, it's 2 to the 6th. Let's rewrite this as 2 to the 6th. Now what do we have? I have 2 to the 6 tenths. 2 to the 6 tenths, changing the radical form into a rational exponent, 6 over 10, times what? X to the 6 tenths, times z to the 4 tenths, all over y to the 8 tenths. Now what? Well, let's reduce our fractions. Don't leave myself much room here, do I? I write too big. You might be saying, no, you're not writing too big at all. Oops, wrong tool. Get the arrow. And let's move this over some. Okay, that should work. Just ignore this stuff down here. So now what? We have 2 to the, well, 6 tenths reduces to 3 fifths. X to the 6 tenths reduces to, think about that, how about 3 fifths? Z to the 4 tenths becomes z to the 2 fifths, all over y to the 4 fifths. And now, if I'm not mistaken, I believe in these problems you were supposed to leave your answers in radical form. Let me verify that. I've lost my page. What page are we on? Oh, I don't know. It's back here someplace. Okay, here we go. This is number 40, and the instructions ask us to it doesn't really make that clear. Oh, I'm wrong. Looking at this. Use rational exponents to write in simplest radical form. Use rational exponents. 6 over 10, 6 over 10, 4 over 10, 8 over 10, to write this in simplified radical form. That's not radical form, so we're not quite done yet. Notice, please, they are all fifths. Let's change colors. They are all fifths, 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 fifths. How convenient. So I can write the fifth root of what? 2 to the third. Hey, let's change 2 to the third into 8, okay? X to the third, z to the second, over y to the fourth, and we're done. We have now taken this original thing, which was a 10th root of all this stuff, and by making use of rational exponents and reducing those fractions, we've now gotten all the way down to a 5th root of something instead. Considerably simpler. And I'm going to check the book here to see if that is indeed exactly what the writers of the book were expecting us to do. Number 40. Yep, that is it. Why do they have... Okay, yes, that is it. Good. All right. Number 42 may be the most tedious and most annoying problem on the entire assignment. Remember, folks, this is an equation. Equations are to be solved. The vast majority of the problems on this review were not equations. This is an equation to be solved. Our job is to find out what x equals. That's different than just simplifying expressions. Up until now, we have an expression. Oh, I skipped one. We'll come back to it. I have an expression, I simplify. I have an expression, I simplify. I have an expression, I simplify. Expression, I simplify. They were not equations. But now I have an equation to be solved. Don't let me forget to go back to that other problem. How are you going to remind me? I don't know. When solving one of these radical equations, do not let these radicals team up on the same side of the equal sign. If these guys get together, they will have a meeting together. They will strategize against you, 2 brains better than 1, and they will come up with a plan to attack and destroy you. Do not allow these 2 radicals to be on the same side of the equation. Get one of them out of there, and you will foil their plans. They will not prevail against you. But you must separate them. So we're going to take this guy, since he is a minus here, we're going to add him to both sides, giving us square root of 7 minus 4x, bring it down. We're adding this to both sides. Don't forget about your 1, that's very important. 1 plus the square root of 3 minus 2x. We now have them safely on opposite sides of the equal sign. They can no longer hurt us. What do we do now? We square both sides. This side's super easy to square. No, it isn't. Yes, it is. To square the side, all you have to do is get rid of the radical. 7 minus 4x. Oh, I guess that was easy. Yes, it was. Now, this side is a little bit trickier. I'm afraid, because we're squaring something that's kind of like a binomial, we have to use FOIL. Or we have to use the shortcut for squaring binomials. Let's use the shortcut for squaring binomials. We squared this side, the radical went away. We squared this side, what happens? And it looks like I'm going to need a little more space here. So let's move number 44 down. Okay, that'll be fine for now. All right. Squaring this guy. How do you square anybody? How do you square A plus B? You square A, then you multiply A times B and double the answer, and you square B. It's as simple as that. So we'll square A. Well, let me see. Last time I checked, 1 squared is 1. Then we will multiply these two and double the answer. That would have been 1 of these guys, but since I'm doubling the answer, I get 2 of these guys. And then I square this guy. Oh, that's easy. How do you square a square root? It cancels, so we now have plus 3 minus 2x. So we squared this. We multiplied these two and doubled the answer. Right there. then I squared this whole thing, which became that. Now I simplify. I've got a few things to put together here. Actually, I just have two things to put together. There's a 1 plus 3. Let's make that into a 4. Oh, watch this trick. I'm going to get rid of the plus 3 and make that into a 4. There. And that's all I can do. Now you say, wait a minute. What good did that do us? Because we still have a radical. That's right. But originally we had 2 radicals. Now we've got it down to just 1. How about that? That's pretty cool. So what do we do now? Well, we do what we always do with radicals. When there's only one of them, we get it by itself. Remember, these guys are dangerous. You can't let them team up against you on one side. And then to finally conquer them, when you only have one left, you've got to get it by itself. So we'll get rid of the 4. Let's subtract 4 from both sides right now. That'll give us 3 over here. 7 minus 4. Gone. And we're going to keep this one for now. Let's add 2x while we're at it. What's negative? Watch out for signs, folks, please. What's negative 4x plus 2x plus 2x? That's going to be minus 2x. Now, when I say get this guy by himself, we mentioned before, I don't recall when it was, maybe it was the last video, maybe the time before, I don't know. But I have mentioned to you before that multiplications can stay. You don't have to, in fact, to get rid of the multiplication, you divide by 2, you would divide that by 2, and you'd have fractions. It's going to be ugly. You don't have to get rid of multiplications. Nice little gift. Yes, additions and subtractions you have to get rid of. But multiplications, it can stay. So now what are we going to do? We're going to square both sides. Why? Because squaring is how you get rid of radicals. So we square both sides again. Yes, we already squared it once, but when you've got these 2 guys here separated by a minus sign, you're going to end up having to square both sides twice. So we take this side and we square it. We take this side and we square it. Yes, it gets to be a bit of a pain in the neck, but that's all right. You can deal with it. And again, I'm going to have to move all this stuff way out of the way. It's very much in the way. These particular kind of problems take a lot of space. Mr. Bear, I'm trying to conserve nature. I don't want to kill any trees, so I didn't do this problem. Okay, come on, this is math. Kill a tree and do the problem. There are plenty of trees. It's a renewable resource. They're planting new ones all the time, so it's okay. All right, on this side, let's go ahead and do the painful part. Squaring a binomial again. Oh, it's not that painful, come on. Square the first term. Multiply the 2 and double the answer. That'll be minus not 6x, but minus 12x. Then square the last term. That's going to be plus 4x squared. Why isn't it minus? Well, what's negative 2x times negative 2x? Positive 4x squared. On this side, we square the square root. It disappears, but wait a minute, don't forget. We're squaring the entire right side of the equation, so we also have to square the 2. 2 squared is 4. Square root of 3 minus 2x squared is 3 minus 2x. Yeah, these parentheses are vitally important because we have to remember we're now going to multiply 4 by both terms. You know the distributive property. You've been studying the distributive property since pre-algebra. So we multiply this out, we get what? 12 minus 8x. Isn't this fun? 9 minus 12x plus 4x squared. It's bringing all that stuff down. Please keep your work organized and work down the page. Keep things in columns. Keep your equal signs lined up. Keep stuff like this lined up so you can see where it came from. You need to be able to go back and trace your work. I need to be able to see what you did, so keep things lined up. All right, we need to now get, oh, notice we have an exponent here. There's a word that is not being introduced and will be introduced on Monday in the next chapter, and that word is quadratic. Because there is an exponent of 2 here, this thing is going to be a quadratic. That x squared means I have to shove everything to the left side and get 0 over here. How do you know that? Because I have an x squared over there. If you've got an x squared involved, you're going to have to shove everything to that side, get 0 on this side. It's one of the things you've got to remember. Alright, so doing that, and while we do that, let's put this in the traditional order. Let's put our 4x squared first. And then I've got a minus 12x, but I'm going to add 8x to that on both sides, because I'm trying to get this guy out of there. So I add 8x, that's going to be gone. Adding 8x here, negative 12 plus 8 is going to be negative 4x. And then I've got to also subtract 12. Subtracting 12 here, it's gone. Subtract 12 here, I'm going to have minus 3. And what's that equal to now? But you can't have 0! Yes, you can have 0. Don't be afraid of zeros. Amazing to me how many students are afraid of zeros. Yes, we subtracted 12, we added 8x, we now have 0 over here. Exactly what we wanted to have. And I'm out of room again. Man. Kill another tree. Okay. Make some space. Stand by. Sorry about this. When I set this up, I had no clue it was going to require this much space. Okay, so my last step now, you'll remember from a previous chapter, what chapter I do not remember, but you'll remember that in a case like this, you factor it. So factoring. And to get the 4x squared, I'm not sure whether this is going to be a 2 times 2 or a 4 times 1. I have not looked at the answer. Let's just go ahead and assume for now it's going to be 2x times 2x. Remember, this is doing FOIL backwards. We want to arrange for the firsts to multiply to give 4x squared. So I'm going to try 2x and 2x. It might be 4x and 1x. We'll find out soon. Then, to get the negative, the only way for your lasts to multiply to give a negative is if 1 is positive and 1 is negative. And the only way to get a 3 is going to be either with a 3 and a 1 or a 1 and a 3. Let's throw it in here and see what happens. Then what do? Then I check the outers and inners. You can't ignore the outers and inners in FOIL. Some folks just think they're happy now. Oh, I'm done. Are we? Have we checked the outers and the inners to make sure it works? Outers, multiply, that's negative 2x. Inners is 6x. Negative 2x plus 6x. Oh, wait a minute. Negative 2 plus 6 is positive 4. I wanted a negative 4. Well, that's good news. That means we guessed correctly except for the signs. This one should have been plus. This one should have been minus. Now I know I'm right. I don't even need to check. But I could. Outers, 2x. Inners, negative 6x. Adds up to negative 4x. We are correct. So we finally get 2 solutions. Do you remember how to do that? Do you remember what I call the glorious shortcut? When you've got 2 binomials multiplied to give 0, you ask yourself, what's it take to make this guy become a 0, and what's it take to make this guy become a 0? And the glorious shortcut is change that sign. It's positive, and then put this guy over the coefficient. That's positive 3/2. And this one will give you negative 1/2. Positive 3/2 and negative 1/2. Now there's a little bit of a danger here because we squared both sides of an equation twice. There is that danger that one or both of those answers may actually not work. Now because this video is already getting kind of long, I'm going to just, instead of plugging those in to see if they work, I'm going to just check the answer here in the book. Sorry. Number 42. You're being lazy. No, I'm just recognizing it's getting late here. Yes, they both work. Negative 1/2 and 3/2 both work. So we're done. We do get 2 answers. Oh, there was that one that I asked. Thank you for reminding me. You were going to remind me to go back to that yellow one back here. This is, please, I believe I mentioned it in the previous video, but once again, there are a lot of very, very important odd-numbered problems that were not assigned. The odds are just as important as the evens. So you'll want to go back and try the odds before the test. Email me if you have questions. This is an unassigned odd that's very important. Much, much easier than the one we just did down here. Much easier. This is a case of get that radical by itself. Get that minus 6 out of there. So we add 6 to both sides. Can I use the eraser method to save some space here? I'm going to add 6 here, it's gone. I add 6 here, I have 6. What do I do now? The only thing left to do now, well, not the only thing, but the main thing now is I've got to get rid of that radical. Well, how do you get rid of a square root? You get rid of a square root by squaring it. Both sides. Because what does a square do to a square root? Poof! Gone. We're left with 5 minus 3x equals 36. Now you know the rest from there. Subtract 5. Negative 3x equals 31. Divide by negative 3, so x equals 31 over negative 3. We'd rather put the negative off on the side. And now it's crashing into another problem there. I'm going to pretend that's not there. Hey, I don't have to pretend it's not there, really. So we get x equals negative 31 thirds. And that's such an ugly answer, I just want to check the book and see if it agrees with me. Number 41 is negative 31 thirds indeed. Oh yeah. Feels good when you get it right, you know? So we did 42. There's 44. 44 snuck in there somehow. This must have been in a section that we deliberately skipped, but I don't remember. Because no place until now have we discussed how to solve for a variable. But you know, it's really the same thing. Trying to solve for e, trying to get e by itself. What's the first thing we see here that's in the way of e being by itself? This nasty radical. How do I get rid of any nasty radical? Square both sides. Square this side, square that side. Why? Because once again, a square and a square root cancel each other out. I'm left with e over m equals c squared. And suddenly it starts to look a little more familiar. One of the most famous equations in the history of man, discovered by Albert Einstein himself. We're trying to solve for e. I need to get rid of division by m, so I will multiply both sides by m. What do I end up with? E equals mc squared. We normally write it that way. E equals mc squared. Didn't look like it at first. When we saw this, it's like, what is that? Well, that is this. Same thing. 46. Ooh, the world of imaginary numbers. I think things actually get a little bit easier now. Remember the concept here. In the real number world, there is no such thing as a square root of negative 49. Do not try to make it make sense. It will not make sense. There is no such thing. There is no real number square root of negative 49. You can't come up with two real numbers that multiply to give negative 49. I should say, you can't come up with a real number which, when squared, when multiplied by itself, gives negative 49. But in the imaginary number world, we think of this as square root of negative 1 times 49, correct? And we know that we can split multiplication and write it as this. And then we lean on that weird definition we have that the square root of negative 1 is known by its shortcut name of I. Square root of negative 1. I'm done. Oh, well, I'm not quite done because we know the square root of 49. Yes, you're required to fix that. Square root of 49 is 7, so we have 7i. We're done. Did we need to go to all this much trouble? No, we didn't need to go to that much trouble. We could have simply said to ourselves, oh, we pop its eye out. I remember that. We get violent. We pop its eye out. Yes, we pop its eye out. The negative goes pa-ching, and when it pops out, pa-ching, it turns into an eye on the outside. And then square root of 49 is 7. What's the square root of negative 16? 4i. Yes, it's that easy. this guy. The I pops out, becomes an, the negative pops out, becomes an I. Don't worry about that negative sign, it just becomes negative I. And square root of 25 is 5. So it's going to be times 5. There's a much, much better way to write that though. It's negative 5I. So we have negative, pa-ching, 5, negative sign, pa-ching, I, negative 5I. The 25 pops out, becomes a 5. The negative pops out, becomes an I. The negative was already out there. It doesn't disappear. This is an interesting case where one might think that the negatives should cancel. But because it's the world of imaginary numbers, these negatives do not cancel. We just get negative 5I. And that one, by the way, is in yellow. It was not assigned. But it's very important. Number 48. Before you multiply imaginary numbers, you must put them both, or I should say put them all, in I form. Otherwise, you're going to get confused and mess up. We've got to put them in I form. So pop its I out, pa-ching! This becomes I times the square root of 6. And we're multiplying by 6I. Let's bring that on down. So what we've done so far, we've popped out the negative, it turns into an I. What's that do? Well, can we do 6 times square root of 6? Not really. We're just going to write that as 6 times square root of 6. But then what happens with this I times I? Too many students on the test neglect that. They just kind of, oh, it's just I. No, it's not. I times I is not I. Is x times x equal to x? No. Is I times I equal to I? No. What is I times I? It's I squared. But what is I squared? By definition, I squared is negative 1. But that can't be. You're forgetting this is the world of imaginary numbers. With imaginary, that is what makes imaginary numbers so fascinating and so useful. The fact that if you square I, you get a negative answer, negative 1. Only possible in the world of imaginary numbers. No place else can you square something and get a negative answer. I squared is negative 1. But don't ask how that can be. They're imaginary. Use your imagination. But, we'll be quiet. So I times I is negative 1. I'm not going to write times negative 1. That's silly. I'm just going to make it negative 6 square root of 6. So the I times I makes my answer negative. But aren't we multiplying a positive by a positive? Yep. And only in the world of imaginary numbers can you multiply a positive by a positive and get a negative. Only in the imaginary world. Now, folks, number 50. Oh, I grow so weary. In this context, as well as in the context of other problems in past chapters, I grow weary of folks using FOIL on this. Is this a multiplication problem? No. Do parentheses automatically mean multiply? No. What's this thing here for? That's a minus sign. This is subtraction. It's not multiplication. Do we use FOIL? Don't be silly. Why would we use FOIL? It's not multiplication. It's subtraction. So we do 3 minus 2. And we do negative 5I minus a minus I. How do you subtract a minus I? You do the opposite. You add I. So I've got negative 5I plus I is minus 4I. I just subtracted both of these terms. I subtracted 2 and I subtracted negative I. So I added I. Negative 5I plus 1 more I is minus 4I. Done. It's subtraction, it's not multiplication. Don't you touch that thing with FOIL. Like, don't put FOIL in the microwave. Don't put FOIL on a subtraction problem. Alright. Graphing negative 3 plus 5I. Oh, how easy can you get? To graph the imaginary number 3 plus 5I, remember, it's not on the real number line. This axis is referred to as the real axis. This is the imaginary axis. This is an imaginary number. It's not on the real number line. We graph it as if it were -3, 5. We graph it at -3, 5. That's not called -3, 5. We graph it like -3, 5, but it's called -3 plus 5i. That is -3 plus 5i. Not on the real number line. It fell off the real number line because it's not real. It's in imaginary territory. Number 54, absolute value of an imaginary number. First of all, think of it like this. Where is that located? It's at -4 plus 3i, someplace around here. What's absolute value mean? It means how far away from 0 is it? Well, how do I know? Easy. Use the Pythagorean theorem. A squared plus b squared equals c squared. So, bottom line, as we've said before, your formula says we just square this guy. We square this guy. We add the answers and take the square root. So we square our -4. We square our 3. We take the square root of the answer. That's going to be the square root of 25, which is 5. Now, if you happen to have a really good intuitive understanding of what's going on here with the, if you were to graph this, you might say to yourself, isn't that just going to be a 3, 4, 5 triangle? Yes, it is. If you happen to notice that, then you can get this one right without even having to do the work. Because you see a 3 and a 4, you know the hypotenuse has to be 5. Or you can use the Pythagorean theorem. Or you can use the shortcut formula for absolute value of a... What is that formula? Absolute value of a plus bi is equal to a squared plus b squared. Take the square root. That's your formula. If you like formulas, there you go. Number 55. Now come on, folks. Is this one multiplication? Yes, it is. This time. There's no plus or minus sign in there. This is multiplication. Is it the parentheses that make it multiplication? No. It's the fact that there's nothing between the parentheses. That is what makes it multiplication. Just like, is this multiplication? Yes. How do you know? There's nothing in between. That makes it multiplication. There's nothing in between that makes this multiplication. Unlike that earlier problem that so many folks mess up on, where they treat this as if it was multiplication when it's actually subtraction. But this guy really is multiplication. So do we use FOIL? Yes, we use FOIL. And these are fun. Firsts, 2 times 3, 6. Outers, 8i. Inners, -9i. Yes, I could have done that part in my head, but I'm trying to make everything crystal clear. Lasts, -3i times 4i is -12i squared. I times I. Oh, don't forget the I times I. I do grow weary of seeing folks forget about the I times I, and they think it's just going to be I. But no, it's I squared. What difference does it make? Huh. What is I squared? -1? Yes, I squared is -1. So this is -12 times -1. What's that -1 do for us? It changes that -12 into a +12. Only possible in the world of imaginary numbers. Now we combine like terms. I see 6 plus 12, I see 18. I see 8i minus 9i, that's -1i. I'm done. Cool thing about this is, when you multiply two complex numbers, a plus bi, when you multiply two complex numbers, you always get another complex number. Pretty cool concept. 56. This is not special yet. Again, FOIL. Firsts, 6. Outers, 4i. we could do this part in the head. Inners, negative 9i. Lasts, minus 6i squared. But you know what happens with that minus 6i squared? The I squared makes it turn into a plus 6. We've got 6 plus 6. We've got 12. We've got 4i minus 9i is minus 5i. Done. Again, a complex number times a complex number always gives another complex number. We don't get trinomials. We don't get trinomials. Number 58. 58 is special. We don't need FOIL. Why not? Because this is an old-fashioned a plus b times a minus b problem. These guys always turn into just a squared minus b squared. But in the world of imaginary numbers, because of the i's, that minus becomes a plus. So the shortcut, when multiplying a complex number by its conjugate, all you do is square this guy, square that guy, whoops, I almost wrote 12, square this guy, and add the answers every single time. Easiest things in the world to multiply. Square this guy, add the answers, and you will always have a real number. That's the cool thing about conjugates. You multiply two conjugates, you always get a real number. You will not have an I involved in the answer. Because the I times I became negative 1, making this into a plus. And the outers and inners canceled, so you'll never have an I in the answer when you multiply conjugates. Square this guy, square that guy, always add the answers. What's down here? Okay, number 60. Ooh, division. These are fun. Division, the trick is, we're not allowed to leave that I in the denominator. So we're going to do a trick. We're going to multiply by a fancy name for 1. We're going to multiply by the conjugate of the denominator. Don't even look up here. You don't need to look at that. We're only multiplying by the conjugate of the denominator. The conjugate of the denominator is going to be 4 minus 2i. Same thing up here, because you've known since 3rd grade that whatever you do in the denominator, you must also do in the numerator. I grow weary again of seeing folks who will do one thing here and do something different up there. What do we get? Hey, let's do the denominator first because it's so easy. These are conjugates, right? How do you multiply conjugates? Square the first term, square the second term, add. Always, every single time. It's glorious. Numerator, oh yeah, you got to use FOIL, sorry. Firsts, 16. Outers, negative 8i. Inners, another negative 8i for a minus 16i. Lasts, positive 4i squared. Positive 4i squared. But what does a positive 4i squared become? A plus 4i squared becomes minus 4. Because I squared is negative 1, it changes the sign. So plus 4i squared becomes minus 4. Now we combine our like terms. 16 minus 4, 12, minus 16i. But one last detail. You can't leave it like that. We have to split it and simplify. Split it and simplify. 12 over 20 becomes, let's see, divide by 4, 3/5. Split it and simplify. 16 over 20 will be 4/5. Done. We divided both terms by 20 and simplified the fractions. And the reciprocal of 1 minus I. The reciprocal of 1 minus I starts off easy. Like, what's the reciprocal of 5? 1/5. Right. So what's the reciprocal of 1 minus I? 1 over 1 minus I. Right. But we can't leave it that way, right? Can't leave the imaginary number in the denominator. So we multiply once again by the conjugate of the denominator. 1 plus I and 1 plus I. These are easy because when you do a reciprocal, you're always going to have a 1 up here. And 1 times 1 plus I is just 1 plus I. Haha, nice. Denominator, square the first term. 1 squared is 1. The coefficient of I is 1. Yes, I'll be out of here in 4 minutes. Thank you. Yeah, it's almost 5 o'clock. I've got to get kicked out of here now. The coefficient of I is 1. So 1 squared is another 1. Add those. Our final answer is 1 plus I over 2. But, hey, let's split it. We've got to put this in proper complex form. 1/2 plus, I don't want to write I over 2. That's awkward. I'd rather write 1/2 I. 1/2 plus 1/2 I. 1/2 plus 1/2 I. And there's something I wanted to show you over here. A couple things. One, folks, you don't get rid of this by multiplying by cubed root of 4 over cubed root of 4. Because that would be cubed root of 16. Do we know the cubed root of 16? No, we don't. So what are you going to do? Consider that 4 to be a 2 squared. Then you say to yourself, if only, instead of being a 2 squared, if that were a 2 cubed, then that would cancel. Yes, if only this were a 2 cubed. Oh, well, how about if I multiply by another cubed root of 2? What's that give me in the denominator? Now I have cubed root of 2 times 2 times 2. 2 cubed. Up here I have 6 cubed root of 2. Alright. Well, what's the cubed root of 2 cubed? It's just 2. We're done. 6. Oh, that's a 3, sorry. 6 cubed root of 2 over 2. Oh, but we have to reduce the 6 over 2. 6 over 2 is 3 cubed root of 2. Slightly easier way to think of it, maybe. You say to yourself, what special number could I multiply a 4 by to make it become a perfect cube? If I multiply that 4 by 2, don't I get a perfect cube? 8. 4 times 2, I can do the cubed root of 8, which is 2. This is a slightly different way of thinking of it. What can you multiply this guy to make it become a perfect cube that I can then paching out? Or rewrite this as 2 squared, and I see clearly that I need just one more 2 so that I can paching it out. Another one here I wanted to look at, some things that were not on the assignment. Oh yes, folks, do not square both sides. If you square both sides to get a 9 over here, you blew it. You don't get rid of cubed roots by squaring. No. How do you get rid of cubed roots? You get rid of a cubed root by cubing. Oh, of course, it's so obvious now. Expect a problem like this on the test. Expect a problem like this on the test as well. Hint, hint, okay? Oh, I hope you're watching this video. So what happens with the cubed root of a cube? Cancels. We're left with y minus 4 equals 3 cubed. That's not 9, it's 27. Add 4 to both sides. Bang. We're done. We're done. Nice. We can check our answer. Back in the original problem, if I put a 31 in here, 31 minus 4, 27. What's the cubed root of 27? 3. It works. It works. Congratulations. And according to my green X here, we're done. All right. That's it. Your test is coming. So be ready for it. And all the details regarding the test are posted in Google Classroom. See you later. Have a good morning, afternoon, or evening, whichever applies.